Let's start by examining our quadratic equation x squared plus 5x minus 1 equals 0. This is an example of a second-degree polynomial equation that we need to solve. To solve this equation systematically, we need to identify how it relates to the standard form of a quadratic equation. The standard form is written as x squared plus bx plus c equals 0, where a, b, and c are numerical coefficients. Let's identify the coefficients in our equation by color-coding each term. This will help us clearly see which number corresponds to which coefficient in the standard form. Looking at our equation, we can now determine the exact values of our coefficients. For the term x squared, the coefficient a is 1 because the term is simply x squared with no other number multiplying it. When no number is written, we understand that the coefficient is 1. For the middle term, plus 5x, the coefficient b is 5. This is directly visible in our equation. And for the constant term, minus 1, the coefficient c is negative 1. Notice how the sign is included as part of the coefficient. Now that we've identified all three coefficients, a equals 1, b equals 5, and c equals negative 1, we have everything we need to apply the quadratic formula. These values will be substituted into the formula to find the solutions to our original equation. Now that we've identified our quadratic equation x squared plus 5x minus 1 equals 0, we've substituted our values into the quadratic formula. Here a equals 1, b equals 5, and c equals negative 1. The expression under the square root is called the discriminant. It's written as b squared minus 4ac. This part of the formula is crucial because it tells us how many solutions our quadratic equation will have. Let's calculate the discriminant step by step for our equation x squared plus 5x minus 1 equals 0. First, we substitute our values from the original equation. Since b equals 5, a equals 1, and c equals negative 1, we get 5 squared minus 4 times 1 times negative 1. We start by calculating 5 squared, which equals 25. This is the first term of our discriminant. For the second term, we multiply 4 times 1 times negative 1. The 1 doesn't change the value, so we're essentially multiplying 4 by negative 1, giving us negative 4. Now we need to subtract negative 4 from 25. Remember that subtracting a negative number is the same as adding its positive value, so 25 minus negative 4 becomes 25 plus 4. Adding 25 and 4 gives us 29 as our final discriminant value. This is the number that will determine how many real solutions our quadratic equation has. The discriminant is a powerful tool because it instantly tells us how many real solutions our quadratic equation has without having to solve the entire equation. There are three possible scenarios for the discriminant. If b squared minus 4ac is positive, the quadratic equation has two different real solutions. If the discriminant equals 0, we get exactly one real solution, which is a repeated root. And if the discriminant is negative, there are no real solutions at all, only complex ones. In our case, the discriminant is 29, which is clearly positive. This means our quadratic equation x squared plus 5x minus 1 equals 0 will have exactly two real solutions. These solutions will be different from each other. Let's visualize how the discriminant works on a number line. This will help us understand the relationship between the discriminant value and the number of solutions. On this number line, the negative region shown in red corresponds to quadratics with no real solutions. The 0 point shown in yellow represents quadratics with exactly one real solution, and the positive region shown in green represents quadratics with two real solutions. The further away from 0, the more distant the two solutions will be from each other. Our discriminant is 29, which falls well into the positive region. This not only confirms that we have two real solutions, but the relatively large positive value suggests that these solutions are quite far apart from each other on the number line. We've calculated the discriminant of our quadratic equation x squared plus 5x minus 1 equals 0 to be 29. This positive discriminant tells us that our equation has two distinct real solutions. In the next step, we'll use this discriminant value to find those exact solutions. Now that we've found our solutions using the quadratic formula, let's verify that they actually work by substituting them back into our original equation x squared plus 5x minus 1 equals 0. Using the quadratic formula, we found two solutions to this equation. These are the values of x that make our quadratic equation equal to 0. To confirm these are actually solutions, we need to substitute each value back into our original equation. If the equation equals 0 when we plug in these values, then we found valid solutions. Let's first check our first solution, x equals approximately 0.19. We'll substitute this value into the original equation and see if we get 0. We substitute 0.19 for x in the equation x squared plus 5x minus 1 equals 0. So we'll have 0.19 squared plus 5 times 0.19 minus 1. Now let's evaluate each term separately. 0.19 squared equals 0.0361, and 5 times 0.19 equals 0.95. Adding 0.0361 and 0.95 gives us 0.9861. Subtracting 1 from this value gives us approximately 0. Due to rounding in our decimal approximation, we don't get exactly 0, but we're very close. Since our result is essentially 0, we verified that x equals 0.19 is indeed a solution to our original equation. The slight difference from 0 is just due to rounding in our decimal approximation. Now let's verify our second solution, x equals negative 5.19. We'll follow the same process to check if this value satisfies our original equation. We substitute negative 5.19 for x in our equation x squared plus 5x minus 1 equals 0. The first term becomes negative 5.19 squared plus 5 times negative 5.19 minus 1. Remember that when we square a negative number, we get a positive result, so negative 5.19 squared equals 26.94, and 5 times negative 5.19 equals negative 25.95. Now we add these terms together. 26.94 minus 25.95 equals 0.99, and 0.99 minus 1 gives us approximately 0. Again, the small difference is due to rounding in our decimal approximation. This confirms that our second solution, x equals negative 5.19, also satisfies the original quadratic equation. Both of our solutions are valid. While our decimal approximations give us results very close to 0, we can also verify our solutions using exact algebraic forms to get a precise result. Let's see how that works. For our first solution, let's substitute the exact form, negative 5 plus the square root of 29, all divided by 2, into our quadratic equation. First, let's square the fraction in the first term. When we square a fraction, we square the numerator and denominator separately. So we get the quantity negative 5 plus square root of 29 squared divided by 4. Now let's expand the squared term in the numerator. We get 25 minus 10 times the square root of 29 plus 29, all divided by 4. And the second term becomes negative 25 plus 5 times the square root of 29, all divided by 2. Let's simplify the first fraction. Adding 25 and 29 gives us 54. So we have 54 minus 10 times the square root of 29, all divided by 4. For the second fraction, we need to convert it to an equivalent fraction with denominator 4 by multiplying both numerator and denominator by 2. Now that our fractions have the same denominator, we can add them together. In the numerator, we get 54 minus 10 times square root of 29 plus negative 50 plus 10 times square root of 29. The terms with the square root of 29 cancel out, and we're left with 54 minus 50, which equals 4, all divided by 4. This gives us 1, and 1 minus 1 equals 0. This confirms that our exact solution, negative 5 plus square root of 29 divided by 2, is indeed a solution to the original equation. Unlike with our decimal approximation, we get exactly 0 when using the exact algebraic form. The algebraic verification for our second solution would follow a similar process. We'd substitute negative 5 minus square root of 29 divided by 2 into the original equation and expand. After simplifying, we would again get exactly 0. We've now verified both solutions to our quadratic equation x squared plus 5x minus 1 equals 0. This confirms that x equals negative 5 plus square root of 29 divided by 2, or approximately 0.19, and x equals negative 5 minus square root of 29 divided by 2, or approximately negative 5.19, are indeed the only two solutions to this equation.